Hello everyone, I am Masih Hossein from Iran University of Science and Technology. In this presentation, we will discuss my master thesis titled Multiscale Simulation of Non-Catalytic Gas-Solid Reactions for Hydrogen-Based Reduction of Iron Oxide using Computational Fluid Dynamic, Machine Learning, and Machine Vision, conducted under the supervision of Dr. Kassiri and advised by Dr. Rezai. First, we will have an introduction to the topic, then we will review the literature, next we will explain the research methodology, and finally we will present the results and conclusions. Iron naturally exists as oxides and must be reduced to obtain pure iron. This reduction can be achieved through two primary methods, direct reduction and blast furnace. In the blast furnace method, coal serves as a reducing agent, while direct reduction employs syngas. Once the pure iron is obtained, it is melted during the steelmaking process. The liquid steel is then shaped into the products such as rebar and steel coils during the casting or finishing stages. My thesis especially concentrates on iron-making phase using direct reduction. In Iran, due to rich natural gas resources, there are about 30 direct reduction plants. These direct reduction plants predominantly are based on Midrex technology. Midrex technology generally consists of four sections: shaft furnace, reformer, recuperator, and some equipments for recycling. The reduction process occurs in the shaft furnace and reformer produces syngas. The iron oxide reduction in the shaft furnace is a multi-scale process. As you can see, on macro scale we have a furnace which is a type of moving bed reactor. On mesoscale we have a porous iron oxide plates. On micro scale we have microstructures and grains of plates. On nanoscale we have atomic structure of iron oxide. The atomic structure is important in our modeling as Vostit has a lattice defect that can create significant errors in simulations. The initial simulation of shaft furnace at the pilot scale was conducted in 1986. Later, Parisian Laborde conducted the first industrial scale simulation for two industrial plants, Gilmore in United States and Siderca in Argentina. This progress conducted until 2018 when Hamade performed a two-dimensional axic symmetric simulation and showed that metallization degree is lower in the middle region of shaft furnace. On the mesoscale, non-catalytic gas-solid models are developed, helping us to determine the chemical reaction rate inside the shaft furnace. From 1955 by Yagi and later in 1962 by Levenspiel, the unreacted shrinking core model was developed, followed by the structural models such as grain model and random pore model, which incorporate structural parameters into reaction rates. Well, to study impact of parameters, we need to look at both the gas and solid phases. In the solid phase, important aspects are the gangue elements, which are the non-iron oxide compounds, along with porosity, tortuosity, and the shape of pellets. For the gas phase, we need to focus on the flow rate, temperature, pressure, and the composition of the gas. Based on our review, we have identified three research gaps. First, the effect of shape had only been studied by Kong in 1998. Second, no study has been done using artificial intelligence. It's the first use of AI tools which applied machine learning and machine vision to analyze reaction behavior. For first time, we combined CFD simulation with machine vision to enhance this analysis. The methodology of these theses is divided into 5 parts. 4 models are the mesoscale and one model on the macroscale. Each model provides specific features for analyzing various reduction parameters. The iron oxide reduction reaction involves 5 phases and includes 3 types of resistance: reaction resistant, diffusion resistant, and a gas film around the pellets. As shown, iron oxide pellets first convert from hematite to magnetite, then to wolfite, and finally to iron. As the reaction progresses, it creates a highly porous environment. In our first model, we use a 3-interface unreacted sugarcane core model for pellets. Since the gas profile inside the pellet changes rapidly, we consider it a steady state and integrate our equation to obtain 2 integration constants. In this model, we have 3 layers: magnetite, wolfite, and iron. Pay attention that hematite plays as an unreacted core. With the derived equations, we can determine the hydrogen and water vapor concentrations in each layer, resulting in 6 equations with 12 constants. By obtaining these constants, we can derive the concentrations as a function of different radii and then use them in the reaction rate and differential equations for the iron oxides. To obtain these 12 constants, we need 12 boundary conditions. This includes 6 conditions for equality of reaction and diffusion, 4 conditions for equal concentrations at different interfaces, and 2 conditions for mass transfer. By writing all 12 conditions, we can use a coefficient matrix to acquire 12 integration constants. In our first model, we use digital image processing techniques to calculate circularity using thresholding methods like erosion and dilation. The further shapes deviate from sphericity, the less contact area we have, making circularity a useful quantitative parameter. In our second model, we use computational fluid dynamics to study the reduction behavior of iron oxide pellets. A thermogravimetric analyzer device is used, which unfortunately is not available in Iran. This device measures the metallization degree based on weight changes during the reaction. We used 4 coupled partial differential equations to study the fluid inside the TJ tube and pellet. The model considers 4 diffusion mechanisms: Knudsen diffusion, molecular diffusion, and a series resistance combination of Knudsen and molecular diffusion, as well as effective diffusion, which considers porosity and tortuosity. Thermodynamically, Oxide does not form at low temperature, below 570 degrees Celsius. This is a crucial detail because it impacts our calculations and modeling. Moreover, due to its lattice defect, Oxide can exist as Fe 0.940 instead of the ideal FeO, which introduces potential errors in our analysis. In our CFD model, we used machine vision techniques. In the real world, machine vision is used for tasks like license plate recognition. It detects plates based on pixel differences, black being 0 and white being 255. In object detection, we have 2 types of segmentation: semantic segmentation, which classifies all objects as one class, and instance segmentation, which identifies different objects within a single class. We use instance segmentation to identify different pellets in an industrial plant and extract their geometry from images for CFD simulation. About 700 images were collected, annotated, augmented, and preprocessed before being fed into the mask or CNN deep network with a ResNet 50 backbone, which produces a mask to identify plate boundaries. The geometry is then imported into Excel and simulated in COMSOL multiphysics. We used both two-dimensional cross-section and three-dimensional models. Validation was done using two parameters, solid conversion and pellet porosity. Porosity validation is rare, but using recent studies by Amok Mishram and Metolina, we could achieve this. Additionally, we use watershed segmentation as a second model of machine vision to correct overlapping and calculate the actual size of pellet using a calibration factor. In the third model of pellet, we use the random pore model to examine structural parameters like pore size. This model includes two coupled partial differential equations and uses the bio number to represent the resistance of product layer, and the TLM modulus to assess the influence of reaction rate and diffusion. In the fourth model, we use machine learning techniques including multi-layer perceptron, radial base function, random forest, supervector machine, alongside an explainable artificial intelligence model based on game theory. This model assesses the contribution of each input and determines which ones have the most significant impact on reaction rate prediction, allowing us to rank the importance of parameters. In the fifth model, we simulated the reduction zone of an industrial shaft furnace. As shown, gas flows as a plug from the bottom and solid particles move from the top. A key part of our study was examining the effect of shape, previously only studied by Kang. We used the Kang reaction rate for the first time in a shaft furnace simulation. We also use a modified ergon equation. The ergon equation is for fixed bed reactors, but a study modified it for moving bed reactors like a shaft furnace. We further improved this equation for our simulation. Now, let's move to the results. As shown in 3-interface unreacted shaking core model, all 4 solid phase profiles change simultaneously. The widest profile is the green line, representing the Vostad layer, indicating it is the controlling phase. The plots below show different resistances, indicating that initially the chemical reaction is controlling. Then gas diffusion becomes the controlling regime. This slide visually shows the different radii. The black layer representing hematite quickly disappears, indicating a fast reaction rate, while the cream-colored Vostite layer is the slowest phase. We validated this model using 17 experimental cases. However, it should be mentioned that in high porosity pellets, we had remarkable errors. This slide shows the digital image processing output using thresholding, where the pellet image is refined through erosion and dilation operations. The circularity is calculated averaging 0.98 for those pellets used in Metolina research. Well, in the second approach, we validated the CFD model using 2 experimental parameters, solid conversion and porosity. The validation was performed using experimental data of Metolina and the correlation equation of Amok Mishra. This animation shows the output of our CFD simulation, where you can see the gas profile inside the pellet. The key point is that hematite has low porosity, and as reaction progresses, the porosity increases. Therefore, the hematite to magnetite reaction initially proceeds in a linear manner. Because of this, we could even use unreacted shaking core models at this stage. However, As the setting becomes more porous, the unreacted shrinking core model, which assumes a sharp reaction front, can no longer accurately represent the process. Therefore, in our model, we use porosity and tortuosity parameters to account for pellet's structure. As you can see, the gas diffuses in, and after the hematite reaction, the process no longer progresses in layers. To further investigate the effect of shape, we distorted the spherical shape into an ellipse. We observed that as the shape deviates from a perfect sphere, the reaction rate increases. We plotted various solid and porosity profiles and observed that the greatest deviation occurred in volatile layer and porosity profile as we move toward elliptical geometry. As we mentioned before, this layer is our controlling layer. Using sensitivity analysis, we found that the error from approaching an elliptical shape compared to a spherical one reached up to 12%. In our machine vision model, we consider different pellets to include them in the simulation. As you can see, images are captured, annotated, and then preprocessed so that our deep model can better identify them. The output of mask or CNN is shown in black and white, and finally, they are simulated in the console environment. In these simulations, when we use watershed segmentation, we were able to incorporate their actual size into the simulation. As shown here, for example, 22 pellets have been identified, with pellet 11 having the largest surface area, resulting in the highest reaction rate. Additionally, the pellet size is also evident here, as pellet 14, being the largest, require more diffusion, leading to a slower reaction rate. Here, the comparison of reaction times is shown, with pellet 11 having the fastest reaction and the pellet 14 taking the longest time. In this slide, the solid conversion profiles are plotted. It is shown that deviation from a spherical shape results in larger surface area. Well, in the random pore model, we use kinetic parameters from Honey research, which is published in 2023, and validated our model with them. The model was solved using the method of line and finite difference for space. Next, we examine various parameters. The first parameter is the psi, which indicates the pore size. As the pore size increases, the reaction rate also enhances, naturally because more surface area is provided. The second parameter is Thiele modulus, also known as a particle size parameter, which represents the ratio of reaction rate to diffusion. When the pellet size increases, the Thiele modulus enlarges, becoming more diffusion controlled. When the Thiele modulus is low, the reaction rate becomes the controlling factor. The next parameter is the bio number, which represents the resistance of product layer. Naturally, the higher resistance, the slower reaction rate. Now it's turn to talk about machine learning. We use Bayesian optimization, which allows us to optimize various hyperparameters simultaneously in our models. For example, in this slide, which is for a radial-based function neural network, the spread and number of neurons were optimized simultaneously. Additionally, we use explainable artificial intelligence to show the importance of parameters at different times. We found that temperature is the most significant parameter. Then, various 3D dimensional profiles were plotted using optimized machine learning models, showing the nonlinear behavior of reaction, particularly with respect to temperature. Now, it's time to talk about the shaft furnace model, where we use shooting technique. Previous model used constant pressure, and a few studies considered an equation for pressure variation. For the first time, we demonstrated the impact of pressure and observed how significantly pressure can affect our outputs. We validated our model with Gilmore shaft furnace, which is located in the United States. This model is the most commonly validated furnace because its data has been well proven to be reliable. In the mesoscale of shaft furnace, we used unreacted shrinking core model. As you can see, there is an unreacted hematite core in this model around which iron is produced and the unreacted core gradually shrinks. When we consider the shape factor of pellets similar to our other studies, we found that the reaction rate increased. The next parameter was pressure. When we increased the gas pressure entering the shaft furnace by 1 atmosphere, we found that metallization reached to 100% 1 meter earlier. This slide provides an overview of my master thesis. As you can see, it resulted into 2 ISI papers at macro scale, 4 ISI papers at mesoscale, 1 review article, and an industrial project in field of hydrogen-based reduction of iron oxide. Thank you for your attention. If you have any question, I'm here to answer them.